Okay, so the join is one of the most well-studied operators in databases. There's literally hundreds of research publications on join operator implementations. Even today, people publish new implementations for joins, both in database systems and in database theory. But the large majority of them focus on equijoins. Equijoins are the most common form of joins, and they're the most important, typically because your database schema, when you do normalization, like Boyce-Codd normal form, fifth normal form, fourth normal form, you basically have key foreign key constraints or something of that sort that does an equality predicate. Like in our Netflix example over here, you have this R and U, and then you have this equality condition, user ID equals UID. So it's an equijoin. Okay? Typically, in practice, a lot of joins are not just equijoins, but also key foreign key joins. But we'll only focus on equijoins. Inequality joins are trickier and more complex to implement, so we're not going to be talking about them. They're also less important because they don't arise that frequently in practice. Okay, we're going to study 4 major implementation algorithms for equijoins. These are the most well-studied, commonly used, typical relational DBMS implementations offer all 4 of these, or at least a subset of these. First is the nested loop join, also called the page or the block nested loop join. The second is an index nested loop join. Third is called a sort merge join. The fourth is called the hash join. The nested loop join is exactly as it sounds. It's a nested loop. The index nested loop is again exactly as it sounds. It uses an index structure if you have it available. The third one, sort merge, again you use external sorting style ideas. Hash join, again you use hash indexing style ideas. Okay, so that's why sorting, indexing, and all of that matters for the operator implementations. Let's start with the nested loop join. The basic idea is what you would think of in an algorithms class. Like the simplest brain dead idea is just do a for loop over the 2 tables you're joining and then get the matching records. So let's say we are joining R and U. That's a running example. R is the ratings table. U is the users table. For each tuple in users, nested for each tuple in ratings, nested if they match on the join attribute, that is, they satisfy the join predicate, then stitch them, and then output those pair of tuples. If any pair of tuples doesn't satisfy, then skip that and then move to the next iteration of the for loop. Pretty simple, right? But we read pages from disk. We don't read one tuple from disk at a time. So small correction here, the nested loop join, page nested loop join, for each page in users, for each page in ratings, retrieve the pages into memory, and then check each pair of tuples in each of these pages. Basically, you're doing the whole cross product. And then if the pair of tuples matches them, stitch them, and then output them. So basically, all you're doing is the join is being implemented as a cross product followed by a selection operation. There's some terminology here for basically calculating the I/O cost of this. The loop that is outside the table that you're doing a loop on is called the outer table. The inner loop, that table is called the inner table. Pretty intuitive. And so the I/O cost of this operation, this implementation, for each page that you read from users, so you read the first page of users, now you're doing a full sequential scan of R. Okay? Next, you've finished that sequential scan of R. The outer for loop goes to the next iteration. The second page of users is read. You're doing, again, another sequential scan of R. And then you repeat this for every page of U. So overall, you read the pages of U one at a time into memory from disk. So that's NU. And then for every page of U, you read all of R sequentially. So that's NU times NR. Okay, so the I/O cost is actually the product of the number of pages in these 2 tables. So clearly, seems like a very expensive way to implement this. Questions? But this is sort of the simplest procedure you can think of for implementing a join such that the 2 tables do not need to fit in memory entirely. Because you're doing a page read of block, you're reading one page of U at a time, you don't need that much memory. You only need 1 buffer frame for reading U. You're reading the pages of R in a sequential scan manner. So you only need 1 buffer frame to read the pages of R into memory. And then you need 1 buffer frame to stitch the records and then write the output. So you need basically 3 buffer frames. One minor thing to note is because you have this asymmetric expression over here, the I/O cost is NU plus NU times NR. This term is symmetric in U and R, but this term is not. So you typically want to have the smaller table as the outer table. Then if you interchange these two, the I/O cost will become NR plus NR times NU. And if NR is larger than NU, that might be slightly larger than this expression. Okay, so it's not going to matter that much because NU times NR is going to trounce this term over here. But it's just marginally lower. Questions? Pretty simple implementation, right? And like we just calculated, the number of buffer pages this implementation uses is just 3. 1 to read the page of U, 1 to read a page of R at a time, 1 to write the output at a time, 1 page at a time. And so just like we did with the sort external merge sort, the next question we're going to ask is, we don't just have 3 buffer frames, we're going to have B buffer frames where B could be in the millions. How do we utilize that? And that's where the block nested loop join comes in, P and LJ. The basic idea is make P and LJ more memory efficient. So you have B buffer frames, how do we make use of them? And just like the blocking idea, the blocked I/O idea we had for external merge sort, that's what we're going to do here. Instead of reading 1 page of the users at a time, which is the outer table, you're going to read a sequence of B minus 2 pages at a time. Okay, so just like with the external merge sort, we read a sequence of B pages from the sorted runs. Here, we are reading a sequence of B minus 2 pages of U at a time. 1 frame is assigned for reading a page of R. One frame is assigned for writing out the output. So you read the sequence of B minus 2 pages. For each page in R, check if any tuple in this page of R matches any tuple of U that is in memory among these pages. So now you're doing, again, a full cross-product comparison, except U is now, the block of U that is in memory is much larger than the page of R. If any pair of tuples match, satisfy the join condition, stitch them, and then write them to the output buffer. And then as the output buffer fills up, flush it to disk, and you get the temporary output. How does this reduce the I/O cost? It reduces the I/O cost in exactly the same way as it did with blocked I/O. Well, technically, the NU goes down by a factor of B minus 2. Because you're reading a sequence of B minus 2 pages of U at a time, the number of times this inner for loop executes reduces by a factor of B. Okay, so the I/O cost here is still NU for reading all the pages of U into memory, B minus 2 at a time. But then the number of times the inner for loop is invoked has dramatically dropped from NU times NR, so it becomes NU over B minus 2 times NR. So this is why the block nested loop join can reduce the I/O cost very substantially compared to the page nested loop join. Is that clear? Now, one thing to note is we are worried mainly about I/O costs and sequential versus random I/Os and stuff, but the CPU cost also needs to be factored into our calculations because query latency depends on both the I/O cost and the CPU cost. The CPU cost for step 3 over here, where we are comparing every tuple of R with every tuple of these B minus 2 pages of U, is an all pairs comparison. Of course, it's in memory, so it doesn't affect I/O. But this all pairs comparison in memory could be quite slow. Your CPU might get clogged by doing those all pairs comparisons for every block of U that you're reading. And so we use the idea from the hash index, basically build a hash table on this block of U that you read into memory. Because you're doing an equi-join here, you can build an equality predicate. So we basically build a hash index, kind of like a hash index, but it's actually a hash table data structure that is entirely in memory, built only on the pages of U that you have read into memory. And now, once you have a page of R that comes into memory, look at the tuples, you iterate over the tuples in the page, and then basically do a hashing on the value of the join attribute in R to probe into the hash table, and then only retrieve the matching records. Okay, because hashing is a constant time operation, you avoid this number of tuples in R, the page of R, times the number of tuples in the block of U. The comparison cost goes down to number of tuples in the page of R times constant. Okay? You basically only retrieve the records that match. You don't do the all pairs comparison with all the other records of U that do not match. That's basically a simple trick for reducing the computational cost of this all pairs comparison in memory. It does not affect the I/O cost yet, but technically it still does because you're building a hash table data structure on B-2 pages. What is the size of the data structure? Recall for the hash index, we talked about if you build a hash table on a file of page length p, the size becomes f times p, where f is your fudge factor, 1.2. And so then what you have to worry about is B-2 has to be divided by f. You cannot read B-2 pages of u to build a hash table in memory. You can only do B-2 divided by the fudge factor pages. So numerator, it goes back to the numerator. And so then now the I/O cost of this whole thing, where you're trading off unnecessary computation for some extra I/O, becomes nu plus f times nu over B-2 times r, nr. Okay, so basically this CPU optimization that you did to avoid the all pairs comparison, you're increasing the I/O cost by a small amount where you have this fudge factor times nu over B-2 instead of just nu over B-2. Is that clear? So that's basically the I/O cost of the block nested loop join where you have this hash table on the block built in memory. But it's still dramatically smaller than the page nested loop, which is nu times nr, right? F is 1.4, B can be in the millions. So what if there's just 1.4 over here? It's nu over millions anyway. So you've reduced the I/O cost by orders of magnitude by doing the block nested loop join. The CPU cost, because B is in the millions, you're doing a huge amount of computations in memory. That's a huge waste of time. So by using the hash table, you've actually saved a lot of computational time. And in the overall latency calculation, the overall time can actually go down if you use the hash table on the block in memory. Okay? So this is how, in some cases, you have to worry about the computational cost of your algorithm's implementation, not just the I/O cost. But in most cases, it's the I/O cost that we have to worry about because I/O cost can trounce computational costs. You have a question? No? Any questions? Okay. Great. Next comes the index nested loop join. In the index nested loop join, the basic idea is as follows. I'm doing a join of two tables, and I know that there is an index on these tables. Is it possible for me to use that existing index? And it's only possible if there is an index, say a hash index or a tree index, on one of these tables that is on the joining attribute. So in our example here, the joining attribute is UID, and let's say I'm giving you that there is an index in the database that's a tree index or a hash index, doesn't matter, on R. And so the index nested loop join exploits this existing index as follows. Again, you do the same kind of for each sequence of B-2 pages of U at a time. You sort the tuples of U in memory. We'll get back to this. And then for each tuple of U that is in memory in this block, you probe into the index based on the attribute value of that tuple. Probe basically is a search operation on the index. The search cost for the index we already saw. So for a hash index, the probing is basically constant time. For a B plus tree index, it's logarithmic time. And if any of these are tuples that you retrieve based on the index matches it, stitch it with this tuple of U, write it out to the output buffer, and then flush it out to the file. Okay, so basically, if there is an index structure that is available that can be used for executing the join condition, you just exploit it. Instead of doing an all pairs comparison, you're basically doing a scan of U, and then for each tuple in U, you're doing a search operation on the index structure on the other table. And the search operations cost depends on the index. And so the overall I/O cost of this implementation, again, you're reading all the pages of U into memory, one block at a time, so that's NU, plus now you're doing an index lookup. So the IR over here is the cost of the index lookup into R. That varies based on whether it's a hash index or a tree index. The number of index lookups you do is the number of tuples of U. Okay, so this is not NU, this is N tuples of U. N tuples of U is typically much larger than NU because you might pack multiple records of U onto a single page. Okay, so for each tuple of U that comes into memory, you look up into the index to get the matching records. The index, the benefit is for these sorts of equality predicates, it prunes the I/O cost. You're not going to be doing an I/O over all of R. And because you're only getting the matching records, you know by definition that the join attributes are matching. So they satisfy the join condition. You will not get these other records that do not match the join condition. Okay, so there is not much extra computation apart from just probing into the index to get the tuples that match, and then stitch it, and then write it out to the output. Now, this looks like a vague expression. What is IR? I said IR depends on the index. It also depends on other properties of the index. Is it a clustered index? Is it an unclustered index for the tree? Now, if you do block, because you're reading a block of U at a time, we call it block INLJ, but the page INLJ and tuple INLJ simply do not make sense. So whenever people say index nested loop, it always means block of U is read at a time. Because otherwise, you'll basically kind of do individual pages of U at a time. It just creates more overhead. OK, now coming back to this question, why did we sort the tuples of U in memory before you do the kind of lookup into the index for those tuples? The answer is it can have an effect on what this I/O cost translates into for latency. Recall that sequential access versus random access, the latency can be dramatically different. Because you have sorted the tuples of U on user ID, and you're probing into the index in the sorted order of user ID for that block, all the matches that occur will occur right next to each other. That means you will be doing effectively a sequential scan on the leaf level of the index. So based on what your buffer replacement is, most of the index pages that you traverse will be cached into memory. So they will be basically 0 I/O cost. And the only I/O cost will be for retrieving the next leaf page. And because a multiple of these tuples might map onto the same leaf page of your index, you might actually have a cache hit for several of these tuples. So the I/O cost will effectively become 0. Okay? This sorting that you do over here exploits the fact that you can actually cache much of the index pages, cache much of the leaf pages, and so the I/O cost expression over here becomes inaccurate. It becomes a very loose upper bound on the I/O cost for the actual execution. The exact I/O cost is very hard to express in closed form, so we're not going to worry about it any further. Okay, so it exactly depends upon the properties of the index, the properties of the buffer replacement policy, so that how many cache hits you have as you traverse the leaf level, it'll change based on that. Now here's another question. What if you're doing hash index? Does the sorting of the tuples on user ID still help if you have a hash index that you're probing into? Yes?
I'd say yes, because you have a bunch of tools and where they all have the same value, so you want to have the result.
That is right. Yep, so the answer is correct. It still helps if you sort the tuples on the matching, on the join attribute, because several records might have repeated values of the same join attribute. Now in this concrete example, user ID is a primary key of user, so you won't have different value. You won't have multiple records with the same value. But in general, an equi-join, the join attribute doesn't need to be a primary key. So that means multiple tuples of U can share the same join attribute. So now when you do the probe onto the hash index, if your join attributes values are the same, you'll be probing into the same bucket page over and over for multiple tuples. You will get a buffer cache hit. The I/O cost will go down to 0 for those tuples. Okay, so the I/O cost can actually get reduced because you're doing the sorting because of cache hits for the index pages and for the bucket or the leaf pages. And so exact I/O cost expression, it's very hard to write down. It depends on a bunch of things. Depends on the distributions of the join attribute values, depends on the buffer replacement policy. But this is a loose upper bound on the I/O cost. Okay? Is that clear? Any questions about how the index is actually helping us with the join attribute and the joining over here? It allows us to do a search, basically an equality search. And that allows us to skip all the records that basically do not satisfy the predicate and only get the records that you want. You're avoiding an all pairs comparison. You're also secondary storage aware because the index structure need not necessarily fit in memory. But you're doing this sorting as essentially as an efficiency hack to exploit the data access pattern on the index. We know the leaf level of B plus tree is sorted, so we don't need to keep jumping back and forth. If we can make it as sequential as possible, the I/O cost can go to 0 because the leaf pages can get cached in buffer memory for that block of U. Same thing with the hash. If you sort, the bucket pages can get cached in buffer memory. So for at least for the next few tuples, you will get cache hits, and you will have 0 I/O cost.